Hi friends, welcome to Zeus online classes. In this episode, we are going to continue with the first chapter number system from 9th standard. In this section, we will look at the decimal expansions of the real numbers and see if we can use this expansion to distinguish between rationals and irrational numbers. Consider an example. Here, we are going to find the decimal expansions of the numbers 10 by 3, 7 by 8 and 1 by 7 and pay attention to the remainders. And in the first case, the remainders are 1, 1, 1 and the divisor is 3. And in the second case, the remainders are 6, 4 and 0 and the divisor is 8. Now in the last case, the remainders are 3, 2, 6, 4, 5, 1 and the divisor is 7. And what have you noticed? And you may have noticed at least 3 things. Firstly, the remainder becomes 0 after a finite stage or they start repeating themselves. And secondly, the repeating string of remainders will be less than or equal to the divisor. Consider the third example. Here, the remainders are 3, 2, 6, 4, 5, 1. And if we continue the division, we will get these numbers as the remainders. And these all numbers are less than the divisor 7. Similarly, as in the case of example 2, that is here we got the remainders as 6, 4 and 0 which is less than or equal to the divisor 8. And consider the example 1, here all remainders are 1 and the divisor is 3 which implies that these repeating remainders are less than or equal to 3. And thirdly, you can observe that if the remainders repeats, we will get a repeating block of entries in the quotient. That is, in the first example, the remainder 1 repeats again and again and look at the quotient, here 3 repeats. And in the third example, if you will continue the division, we will get a repeating block that is 4, 2, 8, 5, 9 again and again. Is this true for only for 3 rational numbers? No, this is true for every rational numbers of the form p by q, where p and q are integers and q not equal to 0. On dividing p by q, mainly 2 things happen. Either the remainder becomes 0 after a finite number of stage or never becomes 0. That is, we will get a repeating string of remainders. Let us look at each case separately. That is, case 1, the remainder becomes 0. Consider the example 7 by 8 that we have discussed above. That is, we have found 7 by 8 is equal to 0.875. That is, after a finite step, the remainder becomes 0. Similarly, we know that 1 by 2 is equal to 0.5 and 1 by 4 is equal to 0.25. That is, after a finite state, the remainder becomes 0. In this case, we will say that the decimal expansion terminates. Now, consider the second case, that is, the remainder never becomes 0. Now, consider the decimal expansions of the number 1 by 3 and 1 by 4. Here, we can notice that there exists a repeating set of remainders which force the decimal expansion to go on forever. In other words, we can say that we get a repeating string of entries in the quotient. And in this case, we can say that the decimal expansion is non-terminating and recurring. That is, in 1 by 3, this will be equal to 0.333 and this will go forever. That is, the decimal expansions of the rational numbers have only 2 choices. It's either they are terminating or non-terminating recurring. And before, we have seen that 1 by 3 is equal to 0.3333 and etc. Here, 3 repeats infinitely many times and usually we will represent it as 0.3 bar. This line shows that the number 3 repeats again and again. Similarly, we have seen that 1 by 7 is equal to 0.142857, 142857. Here, look at this. Here, this set of number repeats again and again. So, this can also be written as 0.142857 and this bar. And this bar shows that these numbers repeats again and again. Consider another number 3.572772. Here 72 repeats infinitely many times. That is, this can be written as 3.572. Here we will write the line above 72, since here 5 never repeats, 72 repeats. So, we will draw the line above 7 and 2 of a rational number. Now, here we will start like this. Let x equal to our given number, that is 0.333 etc. Now, we are going to multiply this number by 10 on both sides. Then we will get 10x is equal to 10 into 0.333 etc., which is equal to 3.333 etc. Now, this number, look at the right hand side, and this number can be expressed like this, that is 3 plus 0.333 etc. And this number is our number x, that is this is equal to 3 plus x. So, our equation will become 10x is equal to 3 plus x. Now, we will solve this equation to find x, that is 9x is equal to 3, that is x is equal to 3 by 9, which is equal to 1 by 3. That is, our decimal expansion can be expressed as 1 by 3, where p is equal to 1 and q is equal to 3 and q not equal to 0. Consider another problem. Show that 1.272727 etc. can be expressed in the form p by q, where p and q are integers and q not equal to 0. So, as in the previous problem, let x is equal to 1.272727 etc. Here, this number is non-terminating recurring decimal expansion. So, as in the previous problem, we are going to multiply this equation on both sides by 10, and we will see what will happen. And so, this will become 10x is equal to 12.72727 etc. So, when we will subtract an x from 10x, what will happen? That particular number has non-terminating recurring decimal expansion. So, this will not help in our problem, right? So, we will cancel this step and we will multiply this number on both sides by 100. So, this will be equal to 100x is equal to 127.272727 etc. And this number can be represented like this, that is 126 plus 1.272727, right? And what is this number? This is our x. So, this equal to 126 plus x, and this implies 100x minus x is equal to 126, that is 99x is equal to 126, and our x will be 126 divided by 99, that is 14 by 11. This is the required rational representation of our number. From the above examples, we have seen that a number whose decimal expansion is terminating or non-terminating recurring can be represented in the form of p by q, where p and q are integers and q not equal to 0. So, let us summarize. That is, the decimal expansion of a rational number is either terminating or non-terminating recurring. Also, a number whose decimal expansion is terminating or non-terminating recurring is a rational number. So, what about the decimal expansion of an irrational number? From the above result, we can say that the decimal expansion of an irrational number will be non-terminating, non-recurring one. Moreover, we can say that a number with decimal expansion non-terminating and non-recurring one, then the number will be a rational number. Consider an example. Let s is equal to 0.10, 110, 1110 and 11110. Clearly, this number has decimal expansion is non-terminating, non-recurring. So, this number S is irrational. Similarly, root 2, pi are irrational numbers, and we can say that their decimal expansion is non-terminating, non-recurring. And you all are familiar with the number pi. What is the speciality of pi? Of course, you know that pi is an irrational number and the decimal expansion is non-terminating, non-recurring. And you know what? Using high-speed computers and advanced algorithms, pi has been computed up to 1.24 trillion decimal places. Now, let's discuss an example. Find an irrational number between 1 by 7 and 2 by 7. Look at that. Look at the decimal expansion of 1 by 7. That is 0.142857 bar. And this bar denotes that this set of number repeats infinitely many times. And similarly, 2 by 7 has a decimal expansion like this. That is 0.285714 bar. And here also, this set of numbers repeats infinitely many times. Now, the question is, we need to find an irrational number between these two numbers 1 by 7 and 2 by 7. And here, we will use the property of decimal expansion of an irrational number. That is, the decimal expansion of an irrational number will be non-terminating, non-recurring one. That is, here we will find a non-terminating, non-recurring decimal expansion number which lies between 1 by 7 and 2 by 7. For an example, consider a number like this. S is equal to 0.150, 1500, 15000, etc. Clearly, this number S lies between 1 by 7 and 2 by 7. Look at the decimal expansion. Clearly, this expansion is non-terminating, non-recurring. So, this is an irrational number lies between 1 by 7 and 2 by 7. Similarly, you can find infinitely many such numbers which lies between 1 by 7 and 2 by 7. So, that's all about today's class. See you all in another episode. Thank you.